Okay, and now we're on to a little bit more with vectors, relative velocity. This whole lesson really is just three examples, but we're going to work through them. They're kind of slow to work through because of what they are. The equations that we have here, that VAB equals VAC plus VCB, that's really important. The whole idea behind relative velocity is that if I find the velocity of two things relative to the same, or the velocity of one thing relative to another, and then velocity of that same thing relative to something else, I can add those together and get the velocity of the one thing relative to the other thing. That sounds really confusing, right? But it's all in this equation, right? You see the VAB equals VAC plus VCB. So that's the velocity of A relative to B. So if I want to relate A and B, but I don't know how A and B are related to each other, but I do know how A is related to C, and I know how C is related to B, then I can relate those two things to find relative velocity. So we're going to see this in practice now in these examples. So let's take a look. Okay. So our first example, it says if a boat can move at 5 meters per second in still water and the current is flowing at 3 meters per second east, what is the velocity of the boat relative to the shore? So I have the velocity, I want to find the velocity of the boat relative to the shore, and that's going to be the velocity of the boat relative to the water plus the velocity of the water relative to the shore. Right, I've got these things. So boat to water, water to shore. If I add these together, then I get velocity of boat to shore. All right, so let's take a look at this. If the boat is moving downstream, so that means it's moving in the same direction as the flow of water. That means that B, W, and WS have the same sign, right? So the velocity of the boat relative to the water is 5, because that's how fast it can move in still water, plus the velocity of the water to the shore, which is 3 meters per second. And I just end up with 8 meters per second. And this is east. They're both in the same direction. East, if east is positive, right? And then for part B, again, I'm using the same equation, but now I'm saying if the boat is traveling upstream. If the boat is traveling upstream, that means it's going this way. So the 5 meters per second, the relative to the water, that's negative 5 meters per second, because the velocity of the boat is going to be in the negative direction. And then plus, the water is still flowing east, right, plus 3 meters per second. It's going to give me negative 2 meters per second. Or I can say 2 meters per second west, however I want to put that. So here's just a basic example, but showing us, kind of illustrating this equation and how it works. All right, so here's number 2. Let's try this one out. Okay, so we have this boat. It can travel 5 meters per second in stationary water. Same boat as the other one. And we still have, this is now 2 meters per second east, and we want to know the current. It's 200 meters wide. So let's just do a little drawing here. This is 200 meters from here to here. And the water is flowing. The velocity of the water relative to the shore is 2 meters per second, and this direction is east. Okay, so now I want to know the boat's velocity relative to the shore. If the boat is aimed northbound, so it's going northbound, 1, where does the boat land? 2, how long does it take? Well, why don't we do number 2 first? Right. What I'm asking, so the boat is here, and it's pointed that way. So the velocity of the boat relative to the water is 5 meters per second northward. Right. Okay, so in terms of going across, it's going 5 meters per second, right? That's the velocity going north, and it's traveling 200 meters. So the time is going to be this distance, 200 meters, divided by the velocity, 5 meters per second. That's it. So this turns out to be 40 seconds. So I do 2 first. And now I want to know how long, where does the boat land? So the idea is, as it's moving this way, the water is moving it this way. So relative to the shore, it's going both north and east. And so now we know it's in the water for 40 seconds. And that allows us now 2 times 40 seconds. The location let's say delta x, how far down the stream it went, is going to be v times t. So that's going to be 2 meters per second times 40 seconds. So this is 80 meters. So it's 80 meters downstream of the place where it left. So that's example A. Example B is different. So we're going to take a look at, we're changing the situation a little bit here. Okay, still the same boat, still the same river, but now we want to know if he wants to land directly northbound, how should he point the boat? Right? In other words, he's starting here and he wants to land here. We know that if he points the boat this way, he ends up 80 meters downstream. But if he wants to end up here, then in what direction here should he point his boat? All right, so here's what I want. I want to add this vector and this vector so that I end up with something that's just in the northward direction. Right? And so I want to add the 2 meters per second plus the 5 meters per second so that I end up with a vector that's pointing just straight north. Right? Notice this makes a right triangle. And so I can just do some trigonometry here, and I can get the angle, and I can get this side here. And so this is going to turn out to be, using Pythagorean theorem, the square root of 5 squared minus 2 squared gives me 4.6 meters per second. And then at the angle of, we can do inverse cosine of 2 over 5. So it's going to be 66.4 degrees north of west. Okay. That's it. And then part 2, how long does it take? So for part 2, you know, the time, same thing, is going to be this distance divided by, divided by the velocity. Now what velocity are we talking about? Well, we're going straight across this way, and so that's the distance, 200 meters. So we're going to be using this velocity, the one that's just pointing in that direction. So 4.6, nope, sorry, this is 200. And that gives me 43.5 seconds. All right. Now example 3. Here's another. All right, we have an airplane and we need it to travel directly east to an airport 1,200 kilometers away. The airspeed is 600 kilometers per hour, and there is a wind and air current of 50 kilometers per hour northbound. All right, so here we're going to use this idea. We want it to go 1,200 kilometers straight east, right? So we want to have this as our velocity vector. But we know that there's a wind of 50 kilometers per hour north. We know that the velocity of the plane relative to the air is going to be 600 kilometers per hour. All right, now we have this thing. Let's make sure this is adding up the right way. The velocity of the plane relative to the ground is equal to the velocity of the plane relative to the air plus the velocity of the air relative to the ground, right? So this is what our setup looks like here. So this is the velocity of the plane relative to the ground, velocity of the air relative to the ground, and the velocity of the plane relative to the air. Right? We can switch these according to the commutative property of addition. So the question is, in what direction should the plane head? Right? Well, in order to do that, we can just find this angle here, right? Or this angle. So if we're finding this angle, then that's the opposite over hypotenuse. So inverse sine of 50 over 600 gives me 4.8 degrees south of east. That means if I'm pointing east, I go 4.8 degrees south of that. 2, the question is, what is the effective speed of the plane? Now I can just do Pythagorean theorem. That'll give me about 598 kilometers per hour. Pay attention to the units here. And it's okay as long as, you know, we're not multiplying these by any other SI units by seconds or anything like that, so we can be doing it this way. C, what is the effective velocity of the plane? Well, 598 kilometers per hour east, right? This is speed, no direction. It's a scalar. Velocity has direction. It's a, look at this, A, B, C. Sorry about that. Don't know the difference between my letters and numbers. Okay, we're adding east because this is a vector, so we're just putting, that's the direction. It says, how long will it take the plane to make the trip? See D. And so for D, now it's, the time is going to be the distance divided by the velocity. And the distance is, let's see, 1,200 kilometers, and divided by 598 kilometers per hour, so that's about a 2-hour trip. And that is the last example, and I believe that is the end of Unit 1. And so your first unit test will be coming up soon. Thanks for watching.